Mr. President, dear Keynote, first of all, thank you very much for the invitation to speak here today at the opening of the academic year. After all, it is a privilege for me, born, raised and educated here in this part of the world. Here you see me getting my master's degree at that time called Technische Hogeschool Twente, my PhD, and I served as a professor for 10 years. But I have been working in industry now for 40 years. 13 years at Philips, and I spent 2 years at their research lab in Silicon Valley, and the last 27 years at ASML. Therefore, it is also my pleasure to talk about my great passion, semiconductors or chips. Semiconductors shape the world we live in today, and semiconductors are critical to solve some of humanity's toughest challenges. For instance, food. With semiconductors, we can increase the production of our farming industry by autonomous monitoring of livestock or crops, by having robots that actually harvest the vegetables out of our greenhouses, where labor shortages become an increasingly challenging problem. But not only on food, semiconductors are also critical to solve the mobility. Today, many of us are accustomed to a semi-autonomous driving car that provides more safety on the roads, but it will not stop here. Fully autonomous driving cars, will provide mobility to those that currently do not have it. Like the blind in the future can summon a car that will bring them to anywhere they like, safely and in time. Last but not least, semiconductors are also critical for the energy transition we are faced with. The green revolution, not only to harvest energy, solar and wind, or store it, but in particular to distribute it through a grid. The grid, probably one of the toughest challenges we face to enable all of these renewable energy things. None of this will be possible without further advancements in semiconductor industry. But let's take a step back and talk about computing. Computing, here you see a nice picture at the left-hand side. The first mechanical computer, Charles Babbage, in the 19th century. Then in the middle, you see the vacuum tube. As a small kid, I used to scavenge them from old TVs. All the way to the top side, right-hand side, the most advanced chip today, the NVIDIA Grasshopper 200, an engine for our artificial intelligence revolution we find ourselves in the midst of. So for decades, for centuries, there has been an enormous progression in the compute power of our industry, and the current semiconductors actually give it another boost and unprecedented capabilities. And not only have we seen huge technical changes, it also fueled a huge industry. The semiconductor industry today, starting from equipment makers like ASML, but also here in the Netherlands, ASMI and BESI, as well as our peers worldwide, Lam, Tel, etc., to semiconductor makers like Intel, Samsung, TSMC in Taiwan, all the way to those that provide content, Google, Amazon, this industry collectively has an earning of about 500 billion euros annually. And it is expected to double in the next decade. So this is an industry with phenomenal power, financial incentive that fuels a phenomenal innovation engine. Here you see an example of what this engine has produced. This is the most, or according to Wikipedia, the second most powerful computer in the world, the Aurora, which is positioned in the Aragon National Lab in the US. This machine is capable to do 10 to the 18th flops. Now you may question, what is that? That is 1 million times 1 million times 1 million floating point operations per second. It is the most powerful computer in the world, one of the most. And such a computer uses a lot of energy. This computer takes about 60 megawatts, which is 30 to 60 of these giant windmills to power it. And it also takes about 100 cubic meters of water per second to cool it, which is a decent-sized river of, to talk in the local units, 10 or 20 dinkels to cool it. You're probably all aware that, large data centers take a lot of energy. But we all do it in our home. Let's look at an average home. It uses about 1,000 watt on average during the day. If you would do a single Google search and to make up for the energy it takes to do a single Google search, you would have to switch off the light in your room for about 10 seconds. If you do a ChatGPT, it becomes even worse. It's about 10 times more energy. It will be turned dark for a minute and a half. But it can get even much worse. I guess many of you will have Bitcoins, and quite a few of you will have enjoyed it, becoming more wealthier by investing in Bitcoins. To mine a single Bitcoin takes about 500 megajoule. You would have to turn your house dark for a week and a half. But luckily, the industry is very aware of this challenge and stepping up to the plate. So at ASML, we have committed to reduce the energy we need to print a single transistor with the latest technology by 3x from 2018 to 2025, and we are well on our way to reach it. Secondly, our largest semiconductor maker in the world, TSMC, Taiwan Semiconductor Manufacturing Company, has shown the world a roadmap that shows an improvement of energy-efficient performance 3x per 2 years for the next 2 decades. So an exponential improvement of the energy we need to do a single calculation. And this is important in order to keep this world sustainable while providing the capabilities we all need. ASML is proud to play a role in this innovative network. And here you see the humble beginnings of ASML. 1984, spin out of Philips. The wooden shed in front of the Philips building is ASML, the beginning of ASML. About 30 people moved into that shed and actually made a difference. So anybody that's still questioning, can we make the difference in this part of the world? Do we have the innovative power to do so? My simple answer is yes. And I would say this company is the proof of it, and not the only proof of it. Over the last 40 years, we have grown to become the largest industry in our industry, lithographic equipment, business-wise as well as technology-wise, the largest player in the world. 20,000 people employed in the Netherlands, a multiple thereof in our supply chain, 40,000 people worldwide. A market cap of 300 billion, which today is 10x what our parent Philips is worth. This company, over the last years, the latest and greatest technology we productized was EUV technology, extreme ultraviolet lithography. It did not come easy, it did not come overnight. It started in the academic world in the 80s. Japan, Kinoshita-san, in America, Bell Labs, Lawrence Livermore Lab, but also here in the Netherlands. Vom Rijnhuizen, Fred Bijkerk was one of the pioneers on the EUV technology. And his group moved to the University of Twente about 7 to 8 years ago, the XUV group, currently led by Marcelo Akkermans, who I visited earlier today, and I'm very encouraged and impressed to see the ongoing drive to get better understanding of nature and translate that into things we can use to provide a better world. And proudly here show you the latest and greatest machine we have built, our EUV High-NA system. It is, I dare to say, the most complex machine mankind has ever realized. Took us 10 years, 10 billion. This machine can print lines as fine as 8 nanometers, which is 20,000 times thinner than the thickness of your hair. There's one in Veldhoven. It's operated by our friends of IMEC, the research institute in Belgium, and we are currently installing them at our customers worldwide. This success of ASML is a success of a collaborative ecosystem. An ecosystem that consists of customers that not only provide us the money, that we share and discuss a long-term roadmap with them, peers that provide the other equipment needed to make chips, knowledge centers like TNO in the Netherlands, and Fraunhofer. I was always very pleased to see a Fraunhofer site here at the University of Twente. But in Germany, of course, there are large Fraunhofer centers, academics, and last but not least, suppliers. I often state it is relatively easy to do an invention. It is very difficult to invent something that others can actually produce. And close collaboration and vicinity of supply next to knowledge centers is critical to our success. This collaborative network generated the machines, as an example, I just shared with you. And the University of Twente certainly played its role in this network. Here you see just a small selection of covers of theses, PhD theses, that were done by the University of Twente, directly inspired by challenges we face at ASML and leading to knowledge and sometimes ideas directly implemented. Many of these come from the XUV group of Fred Bijkerk, currently run by Marcelo. Some of them come from the group from Detlef Loose that also made a major contribution to some of our technologies. And for that, I really thank you very much. Last but not least, I'd like to emphasize our biggest asset collectively are people. People come up with ideas. People make these machines. People service them. People keep them running. It is an unlimited need of highly educated, talented, highly motivated people are critical. Not just from the academics, also from HBO and MBO. Also the ROC is critical to supply the people that are used by the suppliers of ASML, locally, Demcon, Norma, to name just two of them, to enable us to build the equipment we are building. And I very much encourage you and call upon you to continue collectively with us to help to raise the next generation such that within Europe we continue to be relevant. We can live up to the ambition we have in our CHIPS Act, because with this, the future will be bright. Thank you very much for your attention.